Hello, my name is David Ackerman, student number 220310629, and this is the W12 assignment. Let's get started. So here we have the graph and the schematics with all the values given, where the red is the one of the masses, and then the other is the other mass flow, and you can see and the blue is the full 100% of the mass flow. The assumptions are all components are steady at steady flow, meaning that m is constant, the flow of mass is constant. The whole component is at an ideal cycle. The exit at the free water heater and the component is a saturated liquid. The KE potential energy and kinetic energy are negligible. Pressure at the free water heater is inlets are similar, meaning that they're the same, and the pumps and the turbines are adiabatic. These are some of the useful equations that we're going to be using, and here we use table A5 with x equals 0 and then p equals 10. We're using this chart as here as to find all the S's and H's for the entire system. So here we're finding it on table A5. Here, and it's a table, we're using table A6, so it's going through the pump. So we're going to use this formula right here. So here we're just looking at the table A6 with these given values, which is a superheated table. We're going to find the H3 and S3, which is equal to HF and SF. At state 4, which also using A6, we're gonna see that a S4 equals S3 because the assumptions that we made. Right here, we can use that. Plus, we can find the pressure at 4 is 10 MPa. We can then, because it's going through pump 2 right here, we can use the same equation but with a specific volume. And here's A6, so then we're just looking at the value, the finding H5 and S5 using the temperature and the pressure. Here we have to linearly interpolate with the given S5 at state 5 and P equals 0.8. We linearly interpolate and we get H6 equals this number right here. Then we find the state 7, same thing, the temperature pressure, just look at the table A6 and you'd find the values. And state 8, it's a little bit more complicated. We see that um, we use the same S value for S8 equals S7, and then the pressure is 10 kPa. So we see that it's actually it's a mixture. So we have to find the X first, which we get it's equal to this value. And then we have to use this formula to find H8, and we get actually using the original X value, and we get that H8 equals this. Now that we got all the possible S's and H's, we can now continue to solve the problem. We're going to first find the energy balance. We're going to use the energy balance at the free water heater, where we're going to decline this because it's a steady state. We're going to take off Q and W because it's fully adiabatic, and the mass constant through the system. Mass is constant through the system, so um, we we can combine both masses, and eventually we're going to get the HE equals HI. And now we're going to find that because there's a two streams that the mass flow can go through, we're going to see that we're going to have to use this where H3 is the 100% of the mass flow. Y and plus Y1, we can solve for Y since it's the only unknown, and we can find that Y equals 0.205. Now we find that y minus 1 actually equals to 0.795. So we're going to be using that for the rest of the solving of the problems. So the second law of thermodynamics at the turbines and pumps, we're going to neglect the change in enthalpy. And we're going to find that we're going to use the second law and simplifying it for Sgen, it's isentropic, so Se equals Si. We're actually going to find that there's at Sgen for the turbines and pumps, so pump one, pump two, high pressure turbine and low pressure turbine, the Sgen is actually 0. So the second law of thermodynamics at the open free water heater, we're going to then again apply the second law. We're going to negate there's no change Q. We're going to, actually, this is going to be 0. but we're gonna negate Q, and Sgen equals Si again, and then we're gonna find all the flow of the entropies because there's again multiple streams of mass flow, and then we're gonna get that Sgen equals 0.144 kilojoules per kilogram. So that's gonna be the Sgen for the open free water heater. And then for the boiler, we have to apply the energy balance at the boiler, meaning that energy in equals energy out. And yep. So we use all of this. So we simplify it. There's no work. And for the Q, we were solving for Q, so we find that Q equals HE minus HI. And now we plug in every value that we know on this equation right here. Because we had to find the inlets and the exits, and seeing that there's multiple flows of mass, we have to take that into consideration. We're going to plug everything in, and we're going to get the Q equals 333.72 kilojoules per kilogram. Now we can apply the second law of thermodynamics because we couldn't neglect this Q right here. Then we're going to be setting to 0. Then we're gonna isolate for Sgen, and there again there's multiple flows of mass, and when we plug in every known value that we have and with the flow of mass, we're gonna get that Sgen equals 3.74 for the boiler. Thank you for watching.